Today we have a very interesting integral. And to be honest, it doesn't look like that much. I mean, it shouldn't be hard by the looks of it. We have the integral from 0 to pi by 4 of square root tangent x times the square root of 1 minus tangent x. But the thing about integrals and differential equations, it's often quite easy to come up with integrals that have very captivating solution developments, and this integral is one of those cases. It has a very beautiful solution development using some nice tricks and tools. So let's get started. Now I'd like to get started by converting the integrand into some kind of rational function by invoking the substitution of letting tangent x equal u, which implies that the squared secant of x dx equals du. And this further implies that dx equals du divided by the squared secant, which is 1 plus the squared tangent of x. And as per our substitution, the squared tangent is just u squared. So we have dx divided by 1 plus u squared as the new differential element. And as far as the limits are concerned, as x approaches 0, u approaches tangent 0, which is 0. And as x approaches pi by 4, u approaches tangent pi by 4, which is 1. So this implies that I in the u world is now the integral from 0 to 1 of root tangent x turns into root u times root 1 minus u divided by 1 plus u squared du. And we could write this as the integral from 0 to 1 of square root u minus u squared du divided by 1 plus u squared. And now, how exactly do we deal with this new structure? Well, it turns out there's a systematic line of attack to integrals like these, courtesy of one of the all-time greats. I'm talking about Euler himself. So we're going to invoke the Euler substitution here that comes in handy when you have integrals of functions of the root of quadratics. So we have ax squared plus bx plus c as the argument of the square root function. And the substitution depends on exactly what quadratic is in the square root. So in this case, we have u squared minus u, or u minus u squared. And if we call this function g of u, then g of u has two real roots. G of u equal to 0 implies that u could be 0 or 1. So there are two real roots here. So we're going to invoke the Euler substitution of the third kind, whereby we're going to let root u minus u squared equal to u times a new variable t. And now we want to solve for u in terms of t completely. So this implies, terribly sorry about that, this implies on squaring everything, we have u minus u squared equal to u squared t squared. And this further implies that u squared t squared plus u squared minus u equals 0. And now we can factor out the u squared from the first couple of terms, and we have 1 plus t squared minus u equal to 0. Now there are again two roots here. One is u equal to 0, which is useless for us, but the root that is u equal to 1 by 1 plus t squared, that is in fact the substitution we're looking for. So differentiating gives us du equal to negative 2t dt divided by 1 plus t squared squared. Now returning to the integration problem, we have the integral from where to where exactly? Okay, so we're switching from the u world to the t world. So for u to approach 0, we need t to approach infinity. Remember that the substitution we invoked requires t to be positive. And for u to approach 1, we need t to approach 0. So it's the integral from infinity to 0, negative 2 times the integral, that is because of the differential element, and the square root term turned into u times t. And we have the denominator being 1 plus u squared. U squared would be 1 by 1 plus t squared squared. Our differential element here is t divided by 1 plus t squared squared. Okay, cool. And we also have u in terms of t, right? So we could just write this as t divided by 1 plus t squared. Everything looks in order. So we have twice the integral from 0 to infinity, where I switched up the limits to get rid of the pesky negative sign. And we have t squared divided by 1 plus t squared divided by 1 plus t squared squared plus 1 divided by 1 plus t squared squared times this reciprocal of 1 plus t squared squared. So we have some nice cancellation taking place, and that means we now have twice the integral from 0 to infinity of t squared divided by 1 plus t squared, and expanding the denominator gives me the squared function there, gives me 1 plus t to the 4th power plus 2t squared plus 1, which could be written as t to the 4th power plus 2t squared plus 2. And this still looks like an imposing integral, but a nice partial fraction decomposition will render it much easier to our line of attack. So we have twice the integral from 0 to infinity after the partial fraction decomposition that I've written here somewhere. Yeah, we get t squared, terribly sorry about that. We have t squared plus 2 divided by t to the 4th power plus 2t squared plus 2 minus 1 by t squared plus 1, integration with respect to t, of course. Okay, cool. I didn't really need the parentheses. Anyway, so we have twice the integral from 0 to infinity of t squared plus 2 divided by t to the 4th power plus 2t squared plus 2 dt minus the integral from 0 to infinity, twice the integral from 0 to infinity of 1 by 1 plus t squared, terribly sorry about that, dt. And the second integral is the pretty standard arctangent integral, so that means we have pi by 2 for these limits, and twice of pi by 2 is just pi. So we have this integral here that I'm going to call I sub 1. So this implies that I equals twice of I sub 1 minus pi. So our next target here is the integral I sub 1. Pretty sure that there's some real analysis method to solve this integral, but this kind of integral, the nasty kind where you have these quartic polynomials and all that kind of stuff in the denominator of the integrand, yeah, I think complex analysis is the way to go here. So we're going to use the residue theorem and some beautiful contour integration. So let's define the corresponding complex valued function f of z as z squared plus 2 divided by z to the 4th power plus 2z squared plus 2. And what exactly is the contour we're going to use? Well, let's make use of the classic semicircular contour. So here's my complex plane with the real and the imaginary axes. And my contour is going to be the semicircle of radius r. There we go. And we have negative r here, positive r over here. And wait, I should probably move this thing just a little bit. Can I even do that once I have these neat shapes things? Yeah, I can. Why am I overthinking this so much? Anyway, you guys get the idea. Well, the drawings should be a lot nicer. I get that. Anyway, so this is our contour. We're going to call it C, and we're going to call this semicircular arc part of it as uppercase gamma. So we're interested in the integral over the closed contour C of f of z dz, and we know that this is going to be equal to 2 pi I times the sum of the residues of the function f of z enclosed by our contour C. Now, where exactly are these residues located? Well, if we let the denominator of our function equal 0, then we see that we have 4 simple poles. Those are z equal to plus and minus root negative 1 plus I, as well as plus and minus root negative 1 minus I. And of these 4 simple poles, only 2 are enclosed by our contour. So those are z sub 1 equal to root negative 1 plus I, and z sub 2 equal to negative root negative 1 minus I. You can verify that by calculating the arguments of the 4 simple poles. You'll find that only these two fall inside our contour. Okay, cool. So there's not much work left. We just need to calculate a couple of residues and then sum them up and then multiply by 2 pi I and do some fancy math, and there you have it. We have the integral. Okay, so the residue of the function f of z at z equal to root negative 1 plus I equals the limit. We have simple poles here. As z tends to root negative 1 plus I of z minus root negative 1 plus I times the function f of z. Now f of z is z squared plus 2 divided by the denominator in its factorized version would be z minus root negative 1 plus I times z plus root negative 1 plus I times z minus root negative 1 minus I times z minus root negative 1, no, plus 1 plus root negative 1 minus I. Not the prettiest way to write that, but yeah, you get the idea. So we have some nice cancellation taking place, and now we're interested in evaluating the limit. So we have z squared up there, which means we have negative 1 plus I plus 2, and in the denominator, we have, replacing z by root negative 1 plus I, we have to add it with exactly the same thing, so that's twice the term, times root 1 negative 1 plus I minus root negative 1 minus I times root negative 1 plus I plus root negative 1 minus I. So there's some nice algebra taking place here. We can invoke the a squared minus b squared identity. So in the numerator we have 1 plus I divided by twice the square root of negative 1 plus I times, okay, so we have root negative 1 plus I. Terribly sorry about that. I really need to write things more clearly. So we have root negative 1 plus I. Well, I'm trying to write them clearly. My handwriting is just horrible. Anyway, we have root negative 1 minus I. That's become a recurring theme in my videos, to constantly reference my horrible handwriting. But that's why I keep writing everything as I speak. Plus, I sound pretty good, so there's no need of some kind of AI voice. I'm pretty good on my own. Anyway, so we have 1 plus I divided by twice the square root of negative 1 plus I times some nice cancellation taking place. Negative 1 plus I minus or plus 1 plus I. Again, some really nice cancellation, yo. So we have in the denominator 2I times 2, that's a quarter. And the reciprocal of I times 1 plus I divided by root negative 1 plus I. Now, 1 by I equals negative I, which is just very cool. Every time I reference that, I find it extremely cool. So we have a quarter times negative I minus I squared, which is, of course, going to result in us having negative 1 plus I divided by root negative 1 plus I, and we all know exactly what happens next. We have a quarter, wait, I forgot a negative sign because of this thing here. Okay, great. So we have negative 1 quarter times root negative 1 plus I. That's the residue. Terribly sorry about that. The residue of the function f of z at z equal to z sub 1. And now for the other residue, yeah, it's pretty much the same drill. So I'm going to leave this as an exercise to you good folks watching. So we have the integral over the closed contour C, and this can be broken down into the integral over the diameter of our semicircle, which is from negative r to positive r, so that's an integral over the real line, plus an integral over the semicircular arc gamma. And we're interested in the limiting case of r going to infinity. Okay, so that means we have the integral from negative to positive infinity of f of z could be replaced by f of x because we're on the real axis. So we have x squared plus 2 or t squared plus 2, depending on whether you call the real axis the x-axis or the t-axis, whatever, it doesn't matter. It's just a dummy variable. And we have x to the 4th power plus 2x squared plus 2 dx plus this integral over the semicircular arc, the limit as r tends to infinity of the integral over the semicircular arc gamma, that is. And we know that all of this is supposed to equal 2 pi I times the sum of residues of the function f of z. Now, for this term here, we have two residues to calculate. We have two residues to sum, and they both have a factor of 1/4 in them. So we have 2 pi I divided by 1/4 times root -1 minus I minus root -1 plus I. Now I'm going to write these two complex numbers in their polar forms to make life easier for us. So we have some nice cancellation. That is I pi by 2 times, now both these complex numbers have the same modulus, and that is root 2. And we're left with e to the -3i pi by 8 for the first number. And we have, terribly sorry about that, minus e to the +3i pi by 8. And this thing looks awfully familiar. Recall the definition of the sine function from complex analysis. We have sine z equal to e to the iz minus e to the -iz divided by 2i. And that means that 2 pi I times the sum of residues of the function f of z equals I pi by 2 times root 2 times 2i, -2i, that is, -2i sine 3 pi by 8. Okay, cool. We have some nice cancellation again, and the I and -I terms sort of cancel out because, well, we have -I squared, which is +1. So this implies that the integral from negative to positive infinity plus the limit of the integral over gamma as r tends to infinity equals pi times root 2 times sine of 3 pi by 8. Now, this integral here is what I want to turn my attention to. The limit as r tends to infinity of the integral over gamma, I'm going to do this very quickly, equals the limit as r tends to infinity of the integral over gamma of, wait, I just repeated exactly the same thing, whatever. We have z squared plus 2 up top, and we have z to the 4th power plus 2z squared plus 2 integration with respect to z. So downstairs we have a quartic polynomial, and upstairs we have a quadratic one. So in the modulus, we see that the denominator outpaces the numerator, so as r tends to infinity, the entire thing should collapse to 0 in the modulus sense. So we have the limit of the integral over gamma of the absolute value of f of z as r tends to infinity equal to 0, implying that the integral over gamma of f of z equals 0. Okay, cool. So this implies that the integral from negative to positive infinity of x squared plus 2 divided by x to the 4th power plus 2x squared plus 2 dx equals pi times root 2 times sine of 3 pi by 8. And we see that the left-hand side is the integral of an even function over a symmetric interval. So we could just integrate from 0 to infinity and double the result, which implies that we have I sub 1, which is 1/2 of the integral up top of it. So that means we have pi by 2 times the sine that is times root 2, can't forget that, sine of 3 pi by 8. And sine 3 pi by 8 has a nice closed form. I'll leave it to you as homework to fill in the details. We'll get this really nice closed form that is pi by 2 times root 2 plus 2 divided by, no, wait. I seem to have, no, it's fine. We have pi by 2 times the square root of 1/2 plus 1 plus 1 by root 2. Okay, cool. So that's I sub 1. And the target integral was actually twice this integral minus pi. So this implies that the target integral equals, multiplying by 2, we get rid of the factor of 1/2. We could just factor this pi term and some simplification. We get the square root of root 2 plus 2 divided by 2 times root 2 minus 1, which is a very cute little result. It's a nice, cute little result for our integral that warranted a very extravagant solution development. I really enjoyed solving this integral, and I hope you enjoyed the video. Be sure to like and subscribe. Thank you. See you next time.